Hello. So I'm going to tell you about a new framework to simplify propositional formula. And some of you might ask yourself, like, why propositional logic and why simplification? I mean, isn't that an old problem? Like, we all study higher order logic, fuzzy logic, unification, like all these very difficult problems. So it seems like if this should be solved already, and nowadays we have, we all know about SAT solvers that are able to solve huge problems with millions of clauses and hundreds of thousands of variables very quickly. But it turns out that these are not my words, are people working with solvers that said this. So many solvers are in fact a soup of heuristics. The most powerful nowadays, which are learning solvers, are very powerful but opaque, like a black box. No one really knows how to predict the performance because no one knows really what the solver is doing. More recently, we also have had machine learning solvers that produced amazing results, but apparently they don't scale very well. So all of this kind of points that there's more need for reasoning, more reasoning and less search. Another motivation for this talk is automated, quote-unquote, theorem provers, because if you have worked with theorem provers, they're usually less automated than one would expect. And some even nowadays use as a backend SAT solver, so actually they use Surge and the DPLL algorithm. Then, of course, we have the traditional ways of proving propositional formula or simplifying them, like natural deduction or sequence calculus, but they are not systematic enough in many cases. The search space is huge. And of course, things like truth tables, kernel maps, and so on explode very quickly, and they can just handle like not even 100 variables. So we need something more powerful for bigger problems. Then another problem is that most of these techniques, if not all, and especially solvers, they all require that we flatten the formula first. So you cannot just give any formula. It has to be transformed into a normal form, which usually in SAT solving is conjunction normal form. And this not only makes the problems way bigger, but it also adds a lot of redundancy and a lot of redundant variables. And in many cases, it's not even an equivalent problem. It's just equisatisfiable. So to summarize, there's basically a lot of search and a lot of redundancy that could be reduced, could be simplified, substituted by more reasoning. So our solution is generic, is systematic, it guarantees equivalence of problems, and it guarantees that the problem is monotonically reduced, so it never increases because some of these approaches increase the size of the problem. And it also can handle nested formula, so a propositional formula in any shape. So as an example, this is an example of mini-zinc, how it would transform this very, I don't know if you can see my pointer. No, anyway. Like the constraint is like a super simple constraint, and then when it's flattened, it gets just the tiny thing gets this big, and it adds 3 redundant variables, and it puts it like that, and there's still search, when actually that's a super simple tautology that you can prove mathematically like in seconds, and it should be, the result should be that all the solutions are true. Or the absorption law even, I was surprised that it's not simplified automatically either, there's still search going on. So one wonders that if this time, you can imagine a bigger problem where it's formed by many small little parts like this that are very easy, but put together actually create huge problems that mathematically are very simple. So my approach is based on Peirce existential graphs, which is a non-symbolic and non-linear system, diagrammatic way of representing propositional formula, which is in fact equivalent to propositional logic. And it has just 3 elements. So one is the sheet of assertion, so the blank space, which means truth. And then you put the elements in it like you would in a linear fashion. And then you have the cuts, these circles, the ovals, which mean negation. and everything in this space is an implicit conjunction. So basically, the first one you have P and not Q. Because it's not ordered, that is obviously the same as not Q and P. In this case, you have not, everything inside is negated, P and not Q. But this is actually an important shape because obviously this also, we all know, that translates to not P or Q, which is P implies Q. So you can actually see this shape of two circles as an implication. And then obviously you can represent more and more things, but because it's not ordered, it gives a kind of canonical representation that in linear logic you could represent in many ways, and with many negations or implication or not, or if you transform it to C and F, it will look completely different, etc. So Peirce presented this elegant and easy to learn way of working with logic together with a sound and complete deductive system, which is equivalent to the sequent calculus that we all know. I don't have time to go into it, but this is it. Like, it's just these 6 rules, and for example, the double cut insertion or elimination is the same as double negation insertion or elimination, and the rules are very simple and very easy to understand. And just as an example, so for example, this theorem called the splendid theorem, which in symbolic logic takes 43 steps to prove, in Peirce's diagrammatic representation, it's just 7 steps. So you start from the blank space, and then because of the double negation introduction, you can do that, and then etc. The problem is that this has the same problem a bit than sequent, even if it's better in many ways than the classical approaches. It's still, going from the blank space. How do you know that you have to introduce first that and then that? It's not obvious. Like, there's many, from any step you could try many different ways to progress the proof, and like any mathematical proof is not clear. The search space in your head or computationally is huge. So we take another approach. And then the second thing that we built, that we use for our approach, is binary implication graphs, which are also widely known, especially in SAT, which is very obvious. If you have not X or Y, means that X implies Y, and it also means that not Y implies X. So you have this like the graph way of representing binary clauses. So then from these two graphs, we derived this rule, which is a bit ugly to show here, but basically it's easier to see with an example, which is if you have a formula and you have that A implies E, so not E implies A, right? So you can see that the colors connect with each other. So basically, if you have, for example, E, F, G inside, you can see that you can match it with the other clause, and the second condition of the rule applies, which means that you can delete the not G inside the clause, and with the second one, you can match the 3 of them directly. So the first condition applies, so you can delete it automatically. So this, in the classical approach, you would have to first take this formula and flatten it, and then try to apply subsumption or self-subsuming resolution to the whole thing. And if one doesn't work, then maybe you apply something else. But, well, this one is systematic in the sense that, as we will see, you always go from the outside to the inside. So in practice, we have implemented these, and in practice, so this is an example of binary implication graph of a very small problem. So we combined this rule with a widely known rule, which is equivalent literal substitution. So when you have, in the binary implication graph, when you have a strongly connected component, that tells you that those literals are equivalent. So in practice, we maintain a dictionary of equivalences of that, and we condense the binary implication graph, and we have also implemented lazy versions of transitive reduction and finding these strongly connected components, because otherwise, if you implement any of these, like in the previous talk, naively, everything becomes quadratic automatically and very slow. We also represent, we derived our rules from the existential graphs and the binary implication graphs, but we represent it in practice as a directed acyclic hypergraph, which is this representation here, which allows to find things very quickly, and you don't have to traverse the whole formula every time. We give priority to the smallest clauses because they are the ones that have the most power to reduce the other clauses, and then we also combine it with the very easy double cut elimination and this literal substitution that I just mentioned. So the properties of this rule is that because it's reversible, it's equivalence preserving. So while many of the rules used in SAT only preserve equisatisfiability, this one guarantees that you have exactly the same problem with the same solutions. Since it is non-increasing in variables, clauses, and literals, we also know that terminates. You can apply it to any formula. You don't need to transform it before that to a flat version. And in this case, it generalizes all these very widely known techniques in propositional logic and in SAT solving, which many of them are used in SAT solving. So in just one pass, you apply all of this instead of having to combine them in tricky ways or have to first apply one, then another one. You can do everything at once, which simplifies the process a lot. And it can also emulate even more difficult simplification or preprocessing rules, techniques that when restricted to the binary implication graph, which are computationally very expensive, but if we restrict them to this version, can be run until completion. But most importantly, there's no wasted search effort at all in this technique, and it's only reasoning. So we never have to backtrack. There's never a decision literal in the process. So then after this rule, this is the most basic rule, the first rule that we came up with. But after that, we have introduced many other rules which would generalize this one and can achieve even more powerful reductions and generalize all the preprocessing techniques that we have known until now. And one of them, this is just an example of a factor how you can get from several clauses. Actually, you can extract a new unit clause, which then you can propagate very easily, or how we can find equalities between not just literals with literals, but literals with other clauses, and how we substitute that. But this is not in the paper, so I won't go into it. And then, with the implementation, we have also tested it as a proof of concept with a lot of SAT benchmarks, just to prove they can run in all these huge problems with millions of clauses and hundreds of thousands of variables. And we have achieved, SAT problems are known to, industrial problems, to have a lot of redundancy in them. So we achieve pretty big reductions, which is not surprising. And then we have compared it with the equivalence preserving preprocessing that they have in Minisat, and we have achieved some more reduction. But not only that, but if we apply the Minisat equisatisfiable rules after applying our rules, you can achieve even more reductions, up to an 11% more reductions. It is slower than the rules that are out there, but I think that's also not surprising because it's just me implementing this thing on my own, while solvers have been refined by big teams during decades. So it doesn't surprise me either that it's a bit slower. But in any case, it's more robust than, and we have to remember also that it's not the preprocessing inside solving. It simplifies the problem, but it's, again, equisatisfiability is very different from reducing a problem, maintaining equivalence, so all the solutions, and having this, you don't lose any. So basically, it's you conserve all the solutions, so it's good also for model counting and I think it's also understandable that it takes more time because you're actually solving the problem, not just saying if it's satisfiable or not. So in programming, the holy grail is that you state the problem and the computer solves it, but in propositional logic, some say that it's finding a mechanical way to systematize reasoning, or others see it as you give a proposition and then the holy grail is that the computer will tell you an interesting theorem, not just prove what you have to come up in your mind. Again, we already have systematic ways of doing this, like truth tables or the algebra of Boole, but of course, they explode very quickly. And as an example of what I was saying about theorem prover, so this is the vampire theorem prover proof of Peirce's law, which is this very simple law that I had put in Minizing at the bottom. And then you can see how it goes. So it first negates the conjecture, so it will prove by contradiction, then it applies a rule, then it transforms it to ENNF form, it transforms it to CNF form, applies another rule that supposedly has found among many different rules, then it transforms it again to CNF. So there's a lot of transformation and manipulation to be able to apply these rules. Well, in our system, so this is the representation of that rule as an existential graph. And as we said, we start from the outermost smallest clause, so we would propagate the P in the outermost circle. And then following the rules, like you can delete the inner P, then you can delete the double cat, and then you have P or not P. So this is, the blank base is a tautology. So in just 3 steps, you can prove that. If you have also like simple problems that you can get in logic lessons at university, again, like if you have the natural deduction or secant calculus rules, like you have to decide like what way do you go, which inference rule do you apply first, which clever choice of identities do you choose, and if we represent it as an existential graph, that's the thing on the left as an existential graph. Immediately, like we would first, like in the parsing already, we would delete the double cat because it's an obvious transformation, and then we would have C and not B. And then if we propagate one of the two very quickly in just one other step and another double negation elimination, we already reach the point that we have B or not B, so the whole thing disappears. So we don't even have to develop or go into the rest of the potentially very huge problem. And not only that, even better, like because the conclusion was given by someone, or you had to come up with the conclusion. But the beauty of this process is that if you just take the premises, so we wouldn't have the last bit of the existential graph, which is the conclusion. And if you work on that with very, very few steps, you reach the conclusion that A equals B equals C equals true. So actually, which from where you can deduce many other conclusions, not just that C implies B. And then compared to, for example, the DPLL algorithm, the Wikipedia example, and you can see all this testing and backtracking, like all this, oh, let's try if B is 1 or if B is 0. And with with even less number of steps, if you apply our rules. So here, you don't have any clauses smaller than 3, so we would start from the first one where you have the A, not B, and not C. And then a very naive approach would be to just go one by one, right? So you check the first clause with the second, you don't find anything with the third, and so on. But with our representation that I talked about before, which is the hypergraph, I mean, our inner representation in the implementation, you don't even have to go clause by clause. Directly, you would find that you have another clause that has A, B, and C, and then you can match them. And this tells you that you can delete that C. So now you have a clause of size 2, so you give priority to the smaller clause. So then you find where do you have A and B, and then you find that you have it here, and you can delete that B, and then you have again another binary clause which you can propagate, etc. So very quickly and very easily you can deduce already that C has to be true. And then you can propagate this unit clause and delete these bits, and then you can do this. I mean, obviously, in the computer, you don't need all of these steps, but it's to visualize how simple it is, and that there's never a test or a backtrack. It's all equivalent transformations, and then actually you get to the point that this problem is equivalent to A equals B equals C equals D equals true. So you have not only simplified the problem, you have in fact solved the problem. So you know that this is not a solution, this is the only solution of this problem, which is way stronger than just deciding if a problem is satisfiable or not. So our approach is also very important in the field of sharp-SAT, which is model counting, or at least to give lower or upper bounds for the number of solutions. So as a conclusion, which I went very fast, I see. Well, I can give more details or we can have longer questions. So yeah, as a conclusion, our approach reduces the amount of search or wasted search and allows for more reasoning in propositional logic, automated reasoning. Every step every step in our approach is in fact a proof step, so you don't need also to develop proof, like to reconstruct the proof from what you're doing. It also helps understand the problems and the structure of the problems, which can help to develop better solving strategies or better solvers, better ways to sequence methods, and yeah, minimize search in general. You can think of it like Gaussian elimination that we all know, which is simple, is systematic, it simplifies the problem. Of course, it has in this case, like we did the whole complexity study of this rule and the extensions of it, and like DPLA, like the worst time, the worst case time complexity is polynomial, but most of the techniques used nowadays in SAT with huge problems have those kind of worst case bounds, but like in the previous talk, in practice, the problems are quite sparse compared to what they could be, so their strategies, basically you never reach those kind of upper bounds in practice. And also because we never add, because in SAT some of the simplification techniques delete some clauses, but some add redundant clauses or redundant variables. So they actually in practice they have to use heuristics to stop that at some point because it could not terminate. Well, in our case, it's guaranteed to always reduce the problem, so it is guaranteed to terminate. And yeah, as someone said, I don't remember who, but that having a bound is good, but having a ways to characterize all the solutions of a problem reaching that bound is even better. So we think, as a conclusion, that this is a step forward on the quest for automation. And as future work, we could refine our implementation or find someone to refine it. We could also do way more experimentation than what we've done so far. We have already developed a lot of extensions to this simple rule, which are way more powerful and interesting, but we haven't implemented those yet. It would also be very interesting to extend this rule to first order logic, because actually existential graphs have a very, very easy extension to first order logic. So actually all these rules apply obviously to first order logic, but equivalence becomes even easier in that setting. So that'd be an interesting way of research. I'm pretty sure, I mean, this is not, like unit propagation is not refutation complete, but it would also be interesting to study if some of our rules or combination of rules are, or what conditions do we need so that our procedure is refutation complete. It would also be interesting to investigate the link. Actually, existential graphs are very easy to translate to any other propositional formula representation, and there are strong links to A and F or to and inverter graphs. So it would also be interesting to connect those, and it can also help with explainable AI. So that's it.
Thank you, Jordina.
Thank you.
Okay, so any questions?
Well, looks amazing, looks very promising, but I mean, have you done any experiments yet of using it as a preprocessor for existing SAT solvers?
Yeah.
And does it have, or do the SAT solvers just undo a lot of the
So where do I have it?
I mean, obviously, in some cases, it gives you something that's trivially satisfiable or non-satisfiable, but...
I think I had a slide, here. Sorry. I have it now back. So I did do experiments with SAT problems and compared it to the preprocessor of Minisat.
Right, but what I'm asking is not what effect it had on the SAT competition benchmarks, but if you simplify it and then give it to, say the SAT solver that won the SAT competition, does it perform better than it did?
Yeah, it does. Yeah, so after this, here I just show the degree of reduction, but also actually it's very interesting because all the reductions perform faster, but then if we give it to, so if we reduce our output is faster, but if we give the same output to Minisat, which actually just changes the name of the variables, but it's exactly the same problem just with relabeling, then suddenly exactly the same problem can be slower, not that the previous ones, but basically it also shows how, what big impact the heuristics have. So just having variables renamed, the same problem can be solved in few steps, while the other one takes longer. Or even, because usually in SAP processing they use a bounded variable elimination, so they delete a lot of variables in an equisatisfiable way. And that of course reduces the problem very fast, but then sometimes you get problems that were solvable and become unsolvable. So that's also what you get with some of their transformations. But all the reductions have, compared to the original one, go faster. Okay. Just because the degree of reduction is so big. But I'm sure there are problems that's not the case, but it's not our problem. It's not that the reduction is just because how precisely my critique to SAT solving that it's.
But there might be pathological examples where your transformation actually makes some solver do worse on the same problem. I mean, you're saying that so far you found it always improves, but you're not sure whether it's always the case.
I could think of many cases that would be the case, or even like we have in the extension rules, there's some that we allow some specific clauses to be added because actually they allow to traverse the graph or the problem faster. So if you have solvers that can use those clauses, actually that's what learning solvers do. Like they get a stronger clause and then they can solve it faster. So sometimes redundancy helps. But in our case, because we never do any transformation that is just reducing in an equisatisfiable way, actually I think any slowdown that we get is actually because of how the solvers have been implemented and tweaked to be able to be faster at something, but it's not really based on the logics or mathematics, it's just that they have been optimized in a way, or heuristics that works better in something, but it should not, or because then that allows, it cannot be generalized to other problems. So
thank you again, Jordina. I think we can continue the discussion offline.